Hello everybody, welcome to another geometry video. Today we're taking a look at section 1.2, which is all about measuring and constructing some segments. Now we're going to save a lot of the constructing parts for another lesson. However, I want to talk a little bit about how to measure segments, how we can name segments, and how we can actually use a formula to find the distance between two parts of a segment. So let's do it. First things first, we got to talk about what a postulate or an axiom is. Both these words generally mean the same thing. They are just a rule that is accepted without proof. So, for instance, I could make a postulate called the Mr. Strager chocolate postulate, which is, if Mr. Strager eats chocolate, he will have a good day. I don't think many people would say, no, you're a liar, Mr. Strager. It's one of those things that is accepted without a need for us to explain why. And one such postulate is the ruler postulate. So let's say we have 2 points here. And I'm just going to use this as a straight edge, just sort of going off to here. Let's say we've got a line segment. The ruler postulate says that this line segment right here can be measured because we can attribute certain numbers to where these points are. On a ruler, the most common thing to do will be to place one of your points at 0 and then measure where the other point is. So maybe we will mark this off as being at 0. According to the ruler, point B is at 2. The ruler postulate is what lets us attribute numbers to the locations that points or lines are in. So that's what we do. The ruler postulate says that points on a line can be matched with real numbers. This might look a little bit familiar. I mean, think back to middle school. Do you remember seeing something like this up on the wall, where you'd have a bunch of numbers all in a line? Maybe it would continue on and go over to like 3 or 4 or 5, and so on. It's a number line, right? So on a number line, these numbers are called coordinates. You also may remember coordinates from back when we did graphing. And yes, if you look over at the next page, you'll see that we actually do use some coordinates to graph. A coordinate is just a way of representing the position of a point. It's sort of where it's located. So a coordinate is the numbers describing a point's position. And we've used coordinates before in the past. I mean, everybody remembers x comma y, right? This is how we could represent coordinates. So if I have a point floating off in space, let's call this point, I don't know, M. Well, point M will have 2 numbers associated with it. Maybe 1 and -3. Those are an example of its coordinates. And again, it makes more sense when we actually graph them and see where they are. Before we jump into the next couple definitions, I want us to look at the bottom of the page because I want us to review how to read a ruler. It sounds pretty self-explanatory, but it can be a little bit tricky. On the rulers that we use, we have one side that's in centimeters with the smaller numbers, with the more close together numbers, I should say, and one spot that's in inches, where they're more spread apart. Centimeters are easier to measure because on a centimeter ruler, every whole centimeter is marked with a long line. Every half centimeter is marked off with these smaller lines. And all these little tiny dashes are millimeters, or 1/10 of a centimeter. So these are called millimeters. If you want to read in centimeters, you'll put your ruler at 0, wherever you decide 0 to be, and then try and find where the other dot is. And it looks like on this segment, it ends up being at around 5. So that is how we would measure it. Inches is a little bit different because inches have a lot of different marks on them. So I'm going to zoom into the ruler and we'll take a look together. Inches have marks at the whole numbers, just like with centimeters. But there are also half inches, quarter inches, and even eighth inches and 16th inches. Look in between numbers 1 and 2. The part that's exactly right between them, right there, that is the half marker. So 1 1/2 would be right there. Now let's look between the 1 and 1 1/2. Right between 1 and 1 1/2, there is the quarter marker. So this long line here is a quarter. So the dot here would be at 1 1/4 inches. Let's zoom in and look between 1 and 1 1/4. There are 3 little lines in between 1 and 1 1/4. The middle one is halfway between 1 and 1 1/4. That's an eighth. So that longer of the 3 marks is the 8th mark. Finally, the 2 little ones on either side are 16th marks. So when you use an inch ruler, keep in mind that you're going to have to think about it in terms of fractions. Let's do an example to see how we do with measuring. So on the back, we have exercise 1 asking us to use a ruler to measure the length of the segments in inches and centimeters. We're going to do A together, and then B you'll try on your own. So in A, it says to measure it in centimeters, then inches. So I'm going to choose to start with the centimeter side. If I start with the centimeters, I'm going to place my line as close to the halfway point of the dot as is possible. Then I look at the other side and see where the other dot intersects. It's not an exact measurement in this case, so it's okay to round up or round down. In this case, it looks like it goes to 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters, and then it goes to the halfway point between 4 and 5. This means this is at 4 1/2 centimeters. Or, if you wanted to count up all the little millimeters, you could have said there was 4 and 5 millimeters, or 4.5 once again. So this is at 4.5 centimeters. Inches is going to be a bit trickier though, because if we take a look here, it's at a different type of mark. So once again, we place the line as close to the halfway point as possible so that we are perfectly centered on 0. And then we look to see where the next dot is. It's past 1, but it's before 2. So let's take a look at this bit by bit. Is it past 1 1/2? Yes. So it's beyond 1 1/2. From there, it's at this big mark. Well, the other big marks are quarters. So this is 1 1/4, 1 2/4. This, where the dot is at, is 1 3/4. So we can say 1 3/4 of an inch. Very nice. Pause the video and see if you can do part B. I'll show you the answers in just a moment. Hopefully you've had a chance to give it a shot, so let's take a look. If I'm measuring in centimeters, again, I want to center this as close to the middle of the dot as I can, and it looks like this second dot is right before 8 centimeters. It's on one of the smaller marks, so we know that this is going to be in millimeters. So we have 7 and 1, 2, 3, 4, 5, 6, 7, 8 millimeters. 7 and 8 millimeters is 7.8. There we go. Again, if you had a slightly different answer, it's okay. It means that we might have just been slightly different in our terms of accuracy. Let's see if we can do it in inches now. Now in inches, it's a bit weird. It's past 3 inches, but it's on the first little tick mark here. Recall that these tiniest marks are 1/16 of an inch. So this is 3 and 1/16 inches. Very nice. Now we are going to talk about distance. Finding the distance between 2 points sort of looks like this. Let's say we have a little line segment here that starts at point A and ends at point B. Just a line segment. Whoops, I realize I'm zoomed in, so it's kind of hard to see. First of all, what would we call this segment? Well, it has 2 endpoints, so we could name it line segment AB. The distance between A and B depends on where A and B are. So I'm going to name these points x1 and x2. This just represents 2 different unknown numbers, because I don't know where on a number line A and B are. If you want to find the distance between any 2 numbers, x1 and x2, all you've got to do is find their difference. What do I mean by that? We'll see in a moment, but let's take a look at this definition. The distance between 2 points is the absolute value of the difference of their coordinates. The distance between 2 points is the absolute value of the difference between their coordinates. It means you can take these 2 points and subtract one minus the other, take the absolute value of that answer, and you'll find how far apart those points are. In formula terms, if we have points A and B, then the distance of AB is going to equal the absolute value of x2 minus x1. But you could switch these points around if you wanted to. It'll give you the same answer. Now, notice that for the distance here, I didn't actually put a little dash above my AB. We're going to talk about this again in a moment, but I wanted to let you know. When you have that little dash above AB, you are talking about the shape of AB. If you don't, you are talking about the distance. So if you just see 2 letters next to each other, they're not talking about the way the shape looks, they're talking about the distance or how long that line segment is. Let's flip the page very briefly. So this is where it comes time to start talking about something called congruence. Let's say we have two objects that are, for all intents and purposes, the same. What does the same mean? There's a couple of different things that we could interpret the same as. For instance, let's say that I wore the same hat on Monday as I did on Friday. Well, that means that it is a one-of-a-kind hat that I have brought on 2 different days. That is the same. So the same could mean the exact same. When we say that 2 things are the exact same thing, like they're identical, they're just one thing, we use an equal sign. Monday's hat equals Friday's hat. But what if we meant the same in a different way? For instance, let's say that I had a blue hat that I wore, and Miss Barnes had a blue hat that she wore. Maybe these 2 hats look the same shape and size. Well, we would still say they're the same hat. Maybe we bought them from the same store even. However, are they just one object? No, they're still 2 objects, but they're the same. When you're looking at 2 objects and calling them the same thing, we will use what we call a congruence statement. And congruence is a word that means the same. Not like an equal sign, though. It's a symbol that looks like an equal sign with a tilde above it, this little curvy line. When we see that symbol, we're talking about 2 different figures that are still practically the same thing. So anytime that we're talking about the length of 2 things, the length of 2 figures, if the length is the same, we call those 2 equal. If the length of 2 figures is the same, the 2 of them are equal. So maybe we have 2 line segments that are both 7 inches long. Those 2 would be called equal. When you describe the length of a figure, don't include the line over the figure. So line segment JK describes the way a figure looks. Just JK is telling us the length of that figure. So you would say JK equals 4, for instance, and that'd be a reasonable statement. But anytime the appearance of 2 figures looks the same, maybe it's 2 shapes that look to be the same. Anytime we're talking about 2 shapes that look the same, but might be 2 separate figures, we call those 2 figures congruent. The thing is, ultimately, these are notation rules. It's not like you'll get a problem wrong for saying equal when you meant congruent. In fact, if 2 figures are congruent, that means they also have to be the same size, so they're also equal. It's just the way that we like to talk about figures. Figures can be congruent, measurements are equal. Got it? Let's take a look at the previous page where we can do a couple more definitions. So we just talked about congruent. That makes it a lot easier to talk about what congruent segments are. Congruent segments are 2 line segments with the same length. 2 line segments with the same length are called congruent. Maybe I draw 2 line segments on here that are both an inch. So here we have my first one, which I'm going to call line segment AB, and I have another figure up here. I'm going to draw 2 points, and I'm going to call it CD. Both of these line segments were 1 inch long. I know, I used my ruler to make sure of that. So we could say that these two line segments have the same length. AB equals CD. The length of this one equals the length of this one. But because they have the same length and they look to be the same, we would also be able to say that based on just the way they look, these two look the same as well. Line segment AB is congruent to line segment CD. Equal signs will always be used with measurements. Congruences will always be used with shapes. Cool. Next up, I am going to define the word between. I don't think many of us have problems with the word between, but we talk about something very specific in geometry when we say things are between. Between means that when 3 points are collinear, one point is between the others. So something is between 2 points if it is exactly somewhere in the middle between them. It doesn't need to be the exact middle, but it's got to cross on the same line. For instance, if I gave you the following figure, A, B, C, and I put point D up here, B is between A and C. We wouldn't call D between A and C. That's sort of just doing its own thing. Only point B is between, because only point B is on the same line. All right? Let's flip the page once again. We're going to talk about, well, first off, let's talk about this last little bit and these shapes down here. Let's say we wanted to visually show that two things are the same. Again, if we're talking about two figures that are the same, two drawings, two diagrams, we would use a congruent mark. To show it shorthandedly, though, we can use something called a tick mark. Tick marks are a way to visually show that two things are congruent without having to actually write a congruence statement like Strager's hat is congruent to Barnes's hat, or line segment AB is congruent to line segment CD. You can use any mark of the same type on two figures, and it will show that those two things are congruent. For instance, if I wanted to show that this side of the triangle is the same as this side of the triangle, the most common is just to use a slash. Are these two the same? Well, yes. This one looks to be, let's see, it's past the halfway point for inches, but it's on one of those 16th marks. It looks to be, there's 3/4, or 12 16ths. So this is 13 16ths. And this one, if I measure it out, should be, yeah, it's around the same point, 13 16ths. Any two sides of a shape that have a tick mark on them, it means those two sides are congruent. So for instance, in this shape, it's a rectangle. We know that the opposite sides of a rectangle are congruent. So this side is congruent to this side, and well, we need a different mark to show that the top is congruent to the bottom. So you'll sometimes see us use two tick marks. This says the top and the bottom are the same, the left and the right are the same. We can also show that different angles are the same. So this shape is called a pentagon, and in here, you'll see these like curved lines on all the angles. All the angles here are exactly the same. The angles are all congruent. I put smiley faces on all the edges, just as another way of showing you can use whatever you want for a tick mark. It's a little bit intricate, but it does show that all of these sides of the pentagon are also the same length. Very nice. Now, I want you to try out exercise 2 on your own. I'll read out the question, and then we'll do it. It asks us to plot out the following points to make two lines, line segment AB and line segment CD. Then finish the congruence statement by filling in the blanks. So we either need to conclude that AB and CD are congruent or that AB and CD are not congruent. Pause the video and see what you can do. Hopefully you've had some time to try it out. Let's see what we can do together. So let's start by plotting out these points with the given coordinates. So point A is at -3, 4, which we know from middle school and from Algebra 1 that -3 is the first coordinate, so we go 3 to the left. 4 is the second coordinate, and that tells us how much up or down we have to go. So -3, 4 is right here. Most commonly, you'll see me writing the name of the point right next to it, and sometimes you'll see me even write the coordinates, which I'm going to do here. B is at 2, 4, which is right here. C is at 1, 3. That should be right here. There's C. And D is at 1, -2, which is all the way down here. And it asks us to form line segments AB and CD. So to make line segment AB, we are going to just connect the two, and the same with CD. Forgot to put the letter D there. We just connect the two. Bam, just like that. Now, if we want to show that these two things are congruent, we'll need to show that they're the same length. We could do this one of two ways. A ruler is fine, but there's an easier way to do it. We can find the distance between points A and B. Notice that A and B are horizontal with each other. They have the same y coordinate. So really, if I wanted to find the length of AB, I could just use the distance formula. The formula we have for distance right now is the absolute value of x2 minus x1. But again, these can be any 2 points you're comparing. Since the y values didn't change, it stayed at 4, would it make sense to plug in 4's here? I don't think so, because 4 minus 4 is 0. That just tells us that the y coordinates didn't move up or down. Instead, let's plug in the two x coordinates that we were given. I like to go with the second point and then the first. So our second x coordinate was 2. The first was -3. What's 2 minus -3? Well, that's 5. So we take the absolute value of 5, which, if you recall the absolute value, it just makes negative numbers positive and keeps positive numbers the same. The distance between A and B, or the length of line segment AB, is 5. We can do the same with C to D. Again, we just take two of the coordinates and compare them. Again, we have a coordinate that matches. Both of them have an x value of 1. So would it make sense to plug in 1 minus 1 here? Again, no, because we would just be told that the x coordinates didn't change. Instead, let's plug in the y coordinates. Again, I like to plug in the second and then the first, but it doesn't matter what order you plug them in. So I'll do -2 minus 3. Now, it's the absolute value of -2 minus 3, and we know that -2 minus 3 is -5. But remember, the absolute value just changes negative numbers into positive. So this one is 5. That means that the length of AB and the length of CD are the same. Because AB equals CD in terms of their length, we can conclude that line segment AB, which we put the line segment symbol above, is congruent to line segment CD. Because their lengths are the same, the shapes are the same. Very nice. Let's take a look at the next exercise, exercise 3 and exercise 4. It says to label the diagram using the following congruent statements. So we're told, for instance, that line segment AB, which is up here, is congruent to some line segment GF. And there's other line segments that are also told to be congruent. But we have a bunch of blank spaces where the letters are supposed to be on the second shape. Be extremely careful when looking at congruent statements because the order of the letters will tell you what is congruent to what. Let me explain. You see how A is the first part of this line segment and G is the first part of this line segment? Don't know why I got blurry all of a sudden. This is telling us that point A and point G are in the same position across both figures. In other words, point A is congruent to point G. They're the same. Similarly, points B and F are in the same positions in these statements. So B is congruent to F. That means when we're looking at these shapes and we are trying to label these points, make sure that the points match up perfectly. For instance, A is the corner piece, the one that looks like a perfect right angle, on the short line segment. So let's find that on the second image. On the second image, the short line segment is down at the bottom, and this is going to be the right angle. Since A is congruent to G, A has to match with where G is. These two are in the same spot. The same with BF. B is this really wide angle next to A. What's the really wide angle next to G? Well, it's this one. Since B is congruent to F, F goes here. And we can go around the figure again. I mean, look at this. B is congruent to F, just like how C is congruent to E. Since C and E are in the same spots in the congruent statement, we can say that C is congruent to E. C is sort of the tip of this quadrilateral, the one that sticks out. So E is the tip, the one that sticks out. And we could use process of elimination to help us with the last one, or we could just look at these statements. I mean, look at D compared to H. DA is congruent to HG, so the first letter D is congruent to the first letter H. That is where H is. Finally, it says to label the diagram. Whenever we're asked to label a diagram, it also means to mark off congruence marks. So if AB is this line segment up top, we could say it's congruent to GF, the line segment on the bottom. I'll use a single tick mark. BC is congruent to FE, so I'll use 2 tick marks to show BC, 2 tick marks to show FE. CD is congruent to EH. Again, we got to use a new tick mark. I might as well just use 3 lines to show that these sides are congruent. And finally, DA is congruent to HG. You could use 4 tick marks here to show that these sides are congruent. I'm going to use a square. Why would I use a square? I don't know, just to be different. But you can use whatever symbol you like. There's no rules around what symbols you can or can't use. We have now labeled the diagram using congruent statements. Let's take a look at exercise 4. So now we're sort of going backwards. This time we are told what is congruent to what, and we need to write out the actual statements. My recommendation for exercises like this is to start by finding what points are congruent to each other. It's a little bit trickier though on these diagrams because the diagrams are flipped. Let's look at point A. Point A is down here in the corner, but I don't know if that necessarily means point S is congruent to it. The shapes are turned around. So here's my hint for you. When trying to make congruent statements, look at the congruence marks on either side of the point. For instance, A has sort of this triangle pointing towards it and a square. Is there another point that has a triangle and a square on the second diagram? Well, point E has the triangle and the square, therefore, A is congruent to E. Similarly, R, right here, has a single dashed line and a square, just like how S is surrounded by a single dashed line and a square. So R is congruent to S. And the same can be said with B and N. B is congruent to N because both of them are surrounded by a slash mark and a triangle. Once we've got all these, we can now write the statements for the pairs of congruent segments. So let's look at the first segment, the one that has a triangle on it. This line segment is AB. Line segment AB is congruent to, but be careful. A was the first one listed. So what's congruent to A? E. So E has to be the first one listed here. AB, red to blue, is congruent to EN, once again red to blue. Color coding your points can help to distinguish these line segments. Similarly, let's look at the squares. The square goes from A to R. So we can say that AR is congruent to something. Or we could do RA. Order doesn't really matter. Since A is congruent to E, E will be the first letter. And according to our statements, R is congruent to S. So S will be the second. Finally, let's look at these dash marks. The slashes are between B and R. So I'll say line segment BR is congruent to. Again, B is congruent to N. So our statement starts with N. R is congruent to S. So our statement ends with S. That's the set of congruent statements. We've got one more definition to go and one more exercise to go. The final definition is called the segment addition postulate. Again, a postulate is just a statement that doesn't need proving. The segment addition postulate happens anytime you have two segments end to end. Let's say, for instance, I have a line segment AB and a line segment BC. We can compare the lengths of those segments. And we could say that if we put it all together, this would be one line segment, AC. Let's say AB is 3 inches long and BC is 5 inches long. The segment addition postulate says that as long as you've got one straight line segment, you can add together AB and BC. The total length of this segment is 8 inches long. In words, it is, if B is between A and C, then AB plus BC equals the length of the entire segment AC. So, we're basically just putting together two lengths. Let's say in exercise 5, we are told that line segment DE is 23, EF is 35. And we have to find what DF is. My recommended process for this problem is to draw it out. Drawing out a diagram is the best way to represent different figures. So DE was, according to here, DE is 23. Got it mixed up. I'll just write it down here. And EF is 35. So DF, in this case, would be the entire line segment. According to the segment addition postulate, the first segment, DE, plus the second segment, EF, equals that entire line, which we would call DF. So we can add together 23 plus 35 to make, what's 23 plus 35? 23 plus 35 is 58. So we can say the length of DF is 58 units. We don't know if it's inches or centimeters or what, so we'll just say units. Perfect. I want you to pause the video, and I want you to see if you can take on B, C, and D. Be careful with how you draw out part C, and be careful about how you set up part D. Pause the video and give it a shot. So, how'd you do? With part B, we can add together these two people's heights, Haley and Chelsea, to form the unstoppable Halsey. If Haley is 5'1", Chelsea is 5'6", and one is standing on the other's shoulders, together they'd be 10'7". With part C, be careful because it says Bloomfield is between Troy and Walled Lake. So we know the distance between Troy and Bloomfield. We don't know the distance between Bloomfield and Walled Lake. And we also know that the total is 17.6. The way we would solve this is by setting up an equation and solving. Finally, for part D, this was a bit of a long one, but the idea is still the same. LM plus MN equals LN, the entire segment. So 3x plus 8 plus 2x minus 5 equals the entire length of 23. And that's an equation that we know how to solve. That concludes our notes for today, everybody. Thank you so much for listening, and have a fantastic rest of your day.